What we want to do now is to turn our attention towards banked tracks. I want to begin with a couple of demonstrations. One of them is a demonstration, actually is a video that was taken of people who do this sort of thing for entertainment. This may actually be Bangladesh. That's amazing, isn't it? That is a banked track in which circular motion is occurring, but there's more than just a flat surface that's exerting a force on the vehicle. And the roadway itself is exerting part of the force that keeps the vehicle in a path. The next video is a simulation of uniform circular motion on a banked track, showing the forces acting on the object. What's being shown here is the weight force, W, the normal force, N, and the net force that's acting on this car that's on a banked track. So now I'm going to let this video play, and you can see that as the car goes around the banked track, that the net force is always acting towards the center of the circle, and what provides that net force is going to be a component of the normal force that's acting on the car. Now, it may be that friction is an important force for vehicles that are actually on banked tracks, and that's true. Static friction is going to be involved. But if I have a banked track that's at a certain angle and the radius of this circular track is a certain amount, there is a magical speed that I can travel at which static friction is not required at all to keep me in the curve. In other words, if I think of my car on the track, if I'm not moving at all, then static friction would keep me from sliding down the hill. On the other hand, if I were moving too fast, I would tend to slide up the hill, and static friction would hold my car in the road. But there would be a magical speed at which I could travel at, which sliding friction action neither up nor down the track. And it's that speed that we're going to focus on and to solve problems with this sort of application. Let me sketch a diagram of what I mean. I'm looking at a side view of this track, and I have a center of the circle that is towards the left of this particular cross section of the track that I'm looking at. So now I want you to imagine that I'm in my Indianapolis 500 sports car, and I'm driving, and you can imagine the front of the car is driving towards you. So these two blue things that are sitting on that angle of the track are tires. I have my orange sports car. You can see me driving there towards you. I am moving in a circular path, and you're looking at the front of my car driving towards you. We're going to say that this track makes some angle theta with respect to the horizontal. And let's think for a moment of what would happen in several circumstances. First of all, imagine that I'm just parked on this track. Imagine that I'm not moving at all. If there were no motion at all, then friction would keep me from sliding down the hill, down this angle theta, sideways. On the other hand, if I were moving too fast, then you would see that friction might act to keep me from slinging off the edge of the track up the hill. But there's going to be some magical speed, v, with which I'm going to move that's going to be at a number that will keep the frictional force from acting at all. And it's going to be some other force that actually holds me in the circular path. Let's examine the forces that are at work on this car when it's moving at that magical speed, v. I've got two. One of them is the weight. The earth pulls the car downward, and the other is the normal force that acts perpendicular to the track's surface. And what I'm going to claim is that the thing that exerts the centripetal force on the car is going to be a component of the normal force that's acting towards the center of the circle. So what we want to do is we want to figure out what is the relationship between the speed, the radius of curvature of the track, the angle of the track, and the other things that cause this magical speed to come about. Because we're going to want to calculate what that magical speed is based on other characteristics of the track. Here's how we do that. We're going to sketch an XY coordinate system, and tempted as you might be to tilt this one parallel to the track, then that's not what you want to do. You want to keep this one in an upright position, and I think you'll see why shortly. And as we've done so often in this sort of situation, we want to figure out where is theta in this new XY coordinate system that I have sketched. In particular, we're going to be looking for lines that are perpendicular to each other. So I want to notice that this line down here, the base of the triangle that forms the banked track, is perpendicular to the positive y-axis. And I also want to notice that the slant that the car is on is perpendicular to the normal force. So if the angle between the 1 crosshatch and the 2 crosshatch down here is the angle theta, then the angle between the 1 crosshatch and the 2 crosshatch up here must also be the angle theta. And now if I wanted to, I could resolve the normal force into a component that is parallel to and perpendicular to this particular coordinate system. I could resolve Fn to Fn in the x direction and Fn in the y direction. So let's go down and redraw this situation again without it being so busy and figure out what the normal force is in these different components. Okay, so I've tried to sketch a free body diagram showing the angle theta and showing the two forces. The angle between the y-axis and the normal force is the angle theta by this argument that I just gave. And now we want to resolve the normal force into a y component and into an x component. So now I've sketched a diagram in which I have taken Fn and made it the diagonal of a rectangle, and I have resolved it into a vertical part, which is the side that's adjacent to the angle theta. So that's going to be Fn times the cosine of theta, and into a part that is on the opposite side of that angle theta, Fn sine theta. And now I can remove the normal force, and I have its components, Fn cos theta and Fn sine theta, that are acting on this object. Which piece is actually causing the centripetal acceleration? Well, it is the Fn sine theta piece that's causing it. Here's the problem. What is the relationship between the speed, the coefficient of friction, mu s, and the angle and the radius of the track in which no friction is needed to hold the car in the road? Let's figure out what this relationship is. Let's begin with Newton's second law. Newton's second law says the centripetal acceleration is equal to the centripetal force divided by the mass. Next, we recognize that there's a relationship between the centripetal acceleration, the speed of the car, and the radius of the track. The next thing we see is that the thing that provides the centripetal force at this magical speed is the component of the normal force that is towards the center of the circle. This normal force times the sine of the angle theta. Now the next step is a little bit trickier. What I need to recognize is that Fn is not going to be equal to the weight, but there's a component of Fn that is equal to the weight. It is the component that is acting in the opposite direction of the weight. And since the weight is equal to m times g, then I can say that Fn is going to be equal to mg divided by the cosine of theta. And I'm going to feed that result into my centripetal acceleration equation, Newton's second law. So let's feed that in and see what we come up with. Several things happen now at once. On the right-hand side, I will notice that m cancels upstairs and downstairs. And I also notice that I can write sine of theta divided by cosine of theta as the tangent of theta. So let me put that together. Now I've got it. This is it. This is my relationship between the variables if there is no friction needed. And you see that even if the coefficient of static friction is given to you, you don't need it because there's no friction that's involved in this. Let's see this worked out in a particular example. Here's example 37.3. A 1,400 kilogram car is driven at a constant speed of 30 meters per second around a banked track without the aid of friction. The radius of the circular track is 100 meters. Determine the angle of the bank. I've got a diagram here that's drawn, and in this diagram you're looking at the front headlights of a car that's on a bank. The car is driving towards you. The center of the circle is on the right-hand side of this diagram. Let's begin with a free body diagram. When the car is driven at this magical speed without the aid of friction, there are only two forces acting on the car. One of them is the car's weight, and the other one is the normal force that acts perpendicular to the track. As we did before, we want to break the force into components that are parallel and perpendicular to a coordinate system. I'm not going to tilt the coordinate system in this problem. I'm just going to sketch it and then break the normal force into components parallel and perpendicular to that coordinate system. So there's my XY coordinate system. And now I want to find the angle theta in that coordinate system. It takes practice to spot these things. I can see that the horizontal part of the bank and the y-axis are perpendicular to each other. And I can also see that the angle part of the bank and the normal force are perpendicular to each other. And so if theta is the angle between the two crosshatches, then theta must be the angle between the two crosshatches. So now I've located the angle theta. I want to break the normal force into components parallel and perpendicular to that particular axis. If you need some help with this, then what you can draw is a force triangle with Fn at the hypotenuse. You can locate your angle theta in that force triangle and then write the components of the triangle based on the trig functions. So now I want to sketch those components in my force diagram here. And those two components are going to take the place of the normal force. Which one of those is going to be responsible for the centripetal acceleration? Well, it's the part that's pointed towards the center of the circle. It's Fn sine theta. So let's write Newton's second law. Let's recognize that the centripetal force is Fn sine theta and that the centripetal acceleration is v squared over r. Let me also recognize that the weight, which is equal to m times g, and upward component of the normal force, the y component, Fn cos theta, are equal to each other. And from that vertical equation, I can write what the normal force is. The normal force is going to be the weight divided by the cosine of the angle. And I'm going to feed that expression into my other equation. The m's are going to cancel. The sine over cosine is going to become tangent, and I could rewrite this equation. Now what am I trying to find? I know what v is, 30 meters per second. I know what r is, it's 100 meters. I know what g is, it's 10 meters per second squared. I'm trying to find the angle of the bank, theta. So I'm going to solve this equation for theta. Let me take the arctangent of both sides. And now let's put in the numbers. And now I'll feed all of that stuff into my calculator. And I get that the angle is just under 42 degrees. I think what's important is that you see how to set it up, how to sketch free body diagrams, and then to apply Newton's second law. You will get problems like this on a test, so it's important to know how to solve the problem. For now, that's it.